Now, how do we dab into the abilities of these recurrent neural networks that have all of these magnificent dynamical essences, then reservoirs? I just described them a moment ago, but now I think you can see them once again, like and be convinced that it's exactly the same thing we've been talking about all along. That's one thing that you should keep in mind when you're studying recurrent or neural networks in general, that even though they might get very big and there might be different words and like there's usually, and the devils are definitely in the details. But by and large, all of these abstract machine learning style recurrent neural networks, they look the same, even to this day. They change some things specific and they get better. But if you understand where they're coming from, you also see, how the improvement has been gradual rather than abrupt. So it's not like huge inventions. Oh, now people know about GANs or generative adversarial networks, and oh my God, we can reproduce, Obama with the chicken hat. I don't know, but I think it's really important to look at the early examples are sometimes the simplest, and they carry the essence. And so that's why I sometimes stick with them for the moment. And so here you have an input, which is a vector. It's represented as a cylinder full of green numbers. Then you have a reservoir, which is a randomly recurrent neural network with a certain weight matrix WX. And then you have an output that is just basically another cylinder with numbers. Now, the funny thing is that, so this is what I just showed you a moment ago. But in echo-state networks, what you can do is the output weights, instead of changing any of the weights that are in the reservoir, you change only the output weights. And you change them via linear regression. So basically what you have is you can train simply the output weights. The idea is the following. You give an input that can produce something to the network. Then the network does its thing, and it's a confusing thing, can be chaotic thing. But you can, because you have many neurons in the hidden layer, you can extract the information you want by combining it in the output units. So basically you train the output units only, and you train it by linear regression. What does it mean to say that I trained by linear regression? Say, for example, you want to produce, you have one output unit in this network, and you want to produce a sine wave. And as an input, I give you a toggle. If I give you 0, nothing should come out. And if I give you a 1, you want to see a sine wave. So what do? You present the 0 to this network. At first, the network is going to produce a lot of gibberish. And you look at the gibberish, and you use the gibberish as the error from what you wanted to obtain. So you subtract the gibberish from a sine wave and use that error to train the specific output weights to that single unit. Chansu, please.
So is it like we're creating a cost function and like doing, kind of
it's kind of like you're creating a cost function. It's simpler in a sense, because you can use one-shot learning in echo-state networks, because you don't need to backpropagate through the hidden layers. It's just at the level of the output weights. So the linear regression, it's multilinear regression clearly, because you have multiple inputs. So all of the hidden unit activities onto one output unit, which is the other side here. This is the example that I was just talking about. Here we have on the left side, you have an input, and it can take one of these little values here. And I put like an echo state network also available in Canvas so that you can see how this is done, how the training step is done, which is the regression at the output weights. But ultimately, it's just a regression problem. So you have an estimation that should be a function of the input, and the estimation works by standard quadratic linear regression. You have a quadratic loss. You subtract the output from the intended. Nace, come in.
Yeah, so you don't train the dynamical receiver at all, right?
No, exactly.
So how do you know if it's set up correctly, and how do you set
don't.
it up?
So that's the lovely thing about a recurrent neural network. So I should tell you this one thing. The network shouldn't be dead, and the network shouldn't be, let's put it like this, the network shouldn't be too chaotic. The criterion for a valid reservoir, for a valid random network, is that the spectral radius should be smaller than 1, but it should not be too close to 0 either. So the spectral radius of the matrix is basically the dimension with the longest amplitude, the eigen vector with the longest with the largest eigenvalue, if you want to know the specific. So ultimately, when people create the reservoir, they don't do anything with it. They prepare it just so that the matrix has an eigenvalue of a certain radius. I don't know if I talk about eigenvalues here. You guys don't necessarily need to remember, it's just to answer Nace's question. You're familiar with eigenvalues and vectors of a matrix, right, Nace?
Yeah.
Yeah, so the idea is that the largest eigenvalue should be smaller than 1. And that is to prevent that the network gets too chaotic. Too chaotic means basically like flip-flops, that all of the neurons, go from one direction to the other. You can do stuff with chaotic and unpredictable networks, but then they get, their dynamical reservoirs are more specific in a sense. Do I answer your question?
Yeah, but yeah, it's a little bit vague to me, but sure.
So if what part is vague? So creating a random network is vague?
Yeah, well, just like how you would set it up, like how do you know if it's set up in a way you get the results you want?
So this is the beauty of it. It doesn't matter which recurrent neural network you use, just as long as the spectral radius is smaller than 1. That means that there is sufficient propagation in the network, that there is some conservation of the input activity. That's the intuition. Imagine a system of tubes, and these tubes are all haphazardly connected. If you put like a certain amount of water on the top, and then they basically goes and mixes together and comes out of some other tubes, what happens in the middle? It's not as important as how you hook up the output faucets. Just as long as you get sufficient dynamics. It's a bit vague, I think, until you do it, and then it continues to be a bit vague for a long time, because it's like, how is this magic? No, I think that this is the most magical thing that I'm going to tell you today. Chansu.
So you said that we don't change the weights in the dynamical reservoir itself, but at the output level. So does that mean after the dynamical reservoir, we see an arrow to the output? So does that weight that we are changing?
Exactly. So it's only the output weight. So it's only this weight here. So these are tunable. So basically here you have so like you said before, so this is the Y we would like to get. And then this is an estimation of Y that is basically the output of the network itself. So I'm going to put a hat on it. And you have here, this is your error for the training procedure. In quadrat, yeah, it's just like linear regression. Just it is not, it's not just like linear regression, it is linear regression. So I'm not going to belabor here explaining linear regression. If you guys want another lecture on this, we'll have it another time. But here you have an x, and your y hat is basically the network function, which is basically the so this big sigmoid times the summed version of all of the weights times the activities of the neurons inside, right? So like maybe like I'm going to call them A. So this, as usual, plus the theta, is the network function. It comes here. And A's are also related to the inputs, right? So basically, A's are the individual activities here, and X's are the inputs. Maybe I should have thought about notation before I started. So you produce a little bit of an input, and in this case, it's a single unit, and this is actually a true to the letter echo state network with a single input neuron and a single output neuron, and the output neuron then produces sine waves of different frequencies. Basically, you can. This is just a demonstrator of what it can do. Now, I like to think about it in terms of the output to the motor system. So if you have a guy, you know, bowing in his violin, the different types of bows, like a détaché, a martelé, a staccato, they would involve different frequencies and involve different time series at the level of production. I think it's really fun to think about the fact that in the echo state networks, you can train, say, for example, 2 output units, one to produce the angle here and one to produce the angle here, and tell him, I want you to draw a figure of 8 and train the output weights such that an input will produce a 2-unit output that produces a figure of 8. And that's reservoir networks for you. So here you have I think it's a 500 network that's been trained on a figure of 8 is nothing but like 2 embedded sine waves. And you know, you get motor behavior that looks functional at the other end. Cool. Now, I don't say that you have to understand everything. You just, you know, you learned that echo state networks are reservoir networks. You learned that reservoir are created as random matrices, and you don't train that reservoir, and you only train the output weight. So these are the things that you know, should stick to your head. And now, if you want to play more with echo state networks, there is I think in the computing brain, I've copied one of the Jupyter notebook that does that training. So Echo is called Echo IPy network notebook. I'm opening in my Safari here. And then you can look at it by yourself. So it's a minimal echo state network, and you can see what the details are, how to make it in Maze. You can run the network and produce some fun activity. That's basically the guts of your network here. I might have to write more, but I guess that you get it from the skeleton. You get what I was aiming at. So this is going to be available now. Cool. It is quite a magical. I mean, like if you want to, you know, just indulge in a little sense of magic for a little while, and then let's move forward. I think that Hopfield networks also looked very magical to the first people that were thinking about them. But in a sense, they're quite intuitive. I'm going to define them first. And there's not much more that I can do but to define them, as many of these are. I think that it's just really your experience with them that will give you that will make these vague intuitions more concrete. Because ultimately the definition is very concise. The Hopfield networks were created in 1981 by John Hopfield, who was a physicist, and he was studying the properties of spin networks. And a spin network is a network of, say, some magnetic particle that can take one of two values, -1 or +1, and it's connected to its other neighbors, for example, with symmetric force, like, or symmetric magnetism. I influence you like you influence me. Networks like this have the property that they like to settle. So if you randomize the original value of -1s and +1s, say the spins, minus and plus in this network, the network will settle. That means a little bit like, I don't know if you've seen before, if you went to Nemo in Amsterdam, they have one table with magnets underneath, and then you can basically shift the magnets around, and then they're going to be like little spinning needles that are going to spin a little bit, and then later they, after you did your little shifting around with the magnets, the network eventually, or the grid of needles will eventually settle onto a fixed point or onto an equilibrium, right? After, because the network is dissipative, some of the energy that you had put in by moving the magnets moves the needles, but after some time, due to friction and something else, the network settles. So it's a dissipative network. This is the definition. The activity of the next state of the Hopfield network is 1 or 0, or 1 or -1, depending on who you read. Some people use -1, some people use 0, both work. So the activity of unit J in that network, in the next step, is the sum of the activity of the impinging units Vk at time t. I hope you can now recognize when these networks come with completely different choices for words, and they're just the same network every single time. So Vj is activity of unit J. Vk at t is the activity of the another unit in that network in the time step in the past. Tk is what I always call the W, which is the adjacency matrix. Ij is here the theta, the input to the unit J. And if all of that is larger than 0, the activity of your unit is 1. If it's smaller than 0, the activity of unit is 0. So it's kind of like a McCulloch-Pitts unit, only that now we say that the matrix of TJK, the strength of the synaptic input from neuron K to neuron J, are necessarily symmetrical. Okay, so TK, like if there's a connection from neuron 1 to 2, there must be a connection of each of the same weight from 2 to 1. Okay, and with this you can compute the network just as you've computed every other network up until now for the last 3 weeks. Question about this? Now, the training is Hebbian learning, in the sense that if you want to train an input pattern, what you do is you impose that pattern on the network, and your delta W is the same as what we had priorly, which is the multiplication between the, so basically this is the old network that you had before training, and the memory for, so this M here stands for the pattern you want to store. So here, say you have now a network, say a couple of neurons, 1, 2, 3 neurons only. Then you can store patterns on this network that look like this, 0, 1, 0, for instance. And you want to create the weights between them and say this network, this is 1, this is 1, this is 0. The connection between these two neurons is going to be the multiplication between the activities of the memory to be stored. So this network here, this connection here then is going to be reinforced. This link is going to be reinforced, whereas this is going to add to 0. So the connection here, because these guys are correlated, is going to be strong. And in the overall dynamics of the network, if you now give a 0 or a 1 as an input, they will start a little dynamics that will converge onto the pattern that has been stored. Now, this is the trivial example with only simply 3 neurons. The network that you will go through now in the project has a few more. For networks such as these, you have a well-defined error function. Hopfield knew this because he had studied physics, and he knew that spin networks with symmetrical connections have an always negative Lyapunov function. Doesn't matter. What matters is that whatever you put in for a network that has been trained will settle in a fixed point, will always settle. That's because of the symmetric connections. If you have asymmetric connections, you can have a complex reservoir that has spontaneous dynamics. But if you have symmetric connections, then whatever you give into that network as an input will eventually settle. The metaphor was the one here. And you can also read this page. I'm going to give it to you so that you can also see like his own way of explaining this. Now, here, what we, let's see. You can also actually tamper with the pattern yourself. Every pixel here is a unit, and a unit can take 2 values, -1 and 1. When you want to train a pattern on that network, you basically have to create a little pattern, and you have to say remember. And when you say remember, the strength of the connection between the connected pixels is going to be the ones that are participating in the same memory will increase. For example, if my input pattern has this neuron here and this neuron here active, do you see those circles I just made? Then oh boy, just a second. Then the connections between these two neurons in the network is going to be strengthened. And the same thing is true for all of the neurons that are participating in the same pattern, because you've trained them via Hebbian dynamics. So I'm just drawing the fact that this neuron has good connections, strong connections with the neurons that participate in the same pattern as it does. And the same thing is true for every other one of these neurons here. You can initialize the Hopfield network randomly, but once you train it, it will get those patterns imprinted. And once you start the procedure of the dynamics, once you press play on the network, so to speak, when you say like compute the next time step, next time step, next time step, I will converge to the ones that have been stored before. I'm trying to you can also learn your own patterns. Now, the funny thing is what happens when you have something that is both a bunny and something else. If it's close enough to the bunny, it will probably return to the bunny. But if it is closer to something else, it will sometimes get confused. There is a good word for that in English. It's called, it's probably from Greek, it's pareidolia. Pareidolia is the ability of seeing things in clouds, or seeing faces in in cranks, and yeah. So pareidolia, I mean, I think it's a good modern metaphor here. I mean, like, you can start with a random pattern, and then you see the thing that, you know, somehow it reminds you of. You can continue to randomize the pattern here. I'm pressing the button randomize, but when you settle, now this is a relatively simple recurrent neural network, and it certainly has one thing that mathematicians would call trivial dynamics. Trivial dynamics is when they always converge to a fixed point, and it always converges to a fixed point because the energy function is provably always negative. And this is a proof, actually. On this slide, you see the proof of that fact. You don't need to know it, but is the proof the delta energy for whatever time step that the network takes decreases. So the amount of energy that you had from the randomized initial pattern is going to be fading out as you use those symmetrical connections to balance out the asymmetries of the input. This is the best explanation I can give you. Here is another metaphor. So what we do is creating these grooves on an energy field. The dynamics of the network are always going down. So basically, whenever you put a ball at the start, it might select one of these different paths, out of these many, and depending on specifics of your ball, you might fall in one of these attractors. So here we have them representing 4 different attractors. Attractor 1, 2, 3, 4. Those are the final states that you might have saved on the network. And in a Hopfield network, you can save n patterns. And it's an interesting question to ask yourself: how many patterns can you in principle save in these networks? And it's not very many. I mean, reservoir networks can save more patterns. But nevertheless, I think that they stand as a very powerful metaphor for these things. So summary for the Hopfield network is easy. So simple recurrent neural networks have fixed point attractors, even before you train them. But you can't even save these attractors with Hebbian plasticity by reinforcing connections that are coactive. The recurrence leads to spontaneous dynamics in the case of randomly recurrent neural networks. And input often leads to a reduction of dimensionality. It's a little bit like what we're having here in the Hopfield network as well. The network could do anything, but once you give a specific input to it, it goes back to that one thing. And in repository networks, so the attractors of randomly recurrent neural networks can be exploited by linear regression of outputs, such as in echo state networks. The attractors can also be saved. So you can also save attractors at the dynamical reservoir network via teacher forcing, for example. But I didn't talk about teacher forcing today. And I'm not gonna. So attractors can be saved. And this is what we're gonna see in a moment from now. Attractors in the brain, they can be decoded. So if you present a stimulus to a person, the brain dynamics is going to constrain itself to a smaller portion of phase space, or that is, it's going to be simpler than everything that the brain can do. Instead of doing everything, it does one thing. And that one thing has certain statistical irregularities that you can extract from the network via linear regression. Often. There are many algorithms that are used in BCI, but for most of the amazing stuff that you see with cyborg robotic arms, what you have is linear regression first and foremost. The rest is details, and obviously it takes 99% to figure those out, but 99% of the time to figure those out. But this should give you an idea of how we're taking something from even something we don't know about or is random inside that actually produces something meaningful on the other side. Questions about Hopfield networks? The project will be online. And the EcoState network minimal example in the Jupyter notebook, I presume it is already online too.
I have a question.
Yes, please.
So when we have like the pattern for like rabbit and you add like random inputs and it returns back to that pattern of rabbit. So is that like a state of like fixed point? So is that the state of an attractor?
Yeah, so it's going towards the attractor. The attractor is the final state only. What happens between your input and the attractor is the transients, as we call them. Good question. Thank you for the question. So the attractor is only one. You save only one attractor. Everything else is dynamics. So you pressing play is basically saying, given this input, compute one iteration, then from that input, compute another iteration. Those are the dynamics. And the dynamics, the transients, they settle onto a global fixed point attractor. That's vocabulary, right? It's like I'm just deliberately using the right vocabulary, but you get the idea, right? So like it is not. I think that the intuition is even simpler. So I definitely recommend you guys having a look through this entry in Jack Terweiger's blog. I'm going to share with you now over there as in extras. And see this raster plot of the net. So dot. It's I'm wondering where is this no longer. So he has three entries here, and all of the three are very interesting. This is the part 3, and I think that you might even recognize parts of part 2 and part 1. So I'm going to share this with you, and then you can look into this. There are also some spiking attractors here at the bottom, and that's anyways, go through this and you shall have fun. I hope that it will give you a little bit more intuition about how these things happen. Attractors have also been related to decision making, and in fact, that's what you're seeing here in this spiking version of a Hopfield network. You can also do those.
I had a question.
Yeah.
Maybe I missed it, but for what kind of brain functions are attractors useful?
Yeah, so you definitely missed it because I spent like the first half of the lesson talking about this. So here, this is one: sequence generation, memory, pattern completion. I would say the decision making also. And in general, the most general view of what these can be would be generating patterns. Whenever you're producing a memory, you close your eyes, you're thinking about things, your brain is drifting. We would like to think, dynamical systems people like me, that what you're going through are the equivalents of semantic attractors. You think about a banana, then you think about a monkey, then you think about the jungle, then you think about something else. The relationships between those conceptual spaces are acquired by experience to reinforce the likelihood that in the future that sequence is going to appear. Is this clear?
Yeah, thanks.
Yeah, so in more generally, every memory, whether it is a simply a spatial memory, a picture, or if it's a spatial temporal memory, like a motor behavior, those things are encoded via attractors and according to people like me. And I think that nowadays, even according to real hard-nosed biologists, there's a guy, actually shares your name, is Alessandro as well. What's his surname? It won't come to me right now. This has to do with the manifold hypothesis, which I'm going to shortly discuss when we talk about when we meet next time, the manifold hypothesis. Manifold hypothesis is precisely the idea that just as in these randomly recurrent neural networks that I've shown originally, you have these lower dimensional manifolds that are the counterpart of your functional behavior. So instead of having all the neurons active all the time, you need the specific neurons to be active at the right time. And to create these type of sequences, you have to create some sort of, have to carve some sort of energy paths via experience or via even evolution. So you have to carve these energy paths. And so attractors would be like sculpting these rivers. Think about the rain falling on the side of a mountain for many, many years. Then eventually rivers will form. Were the rivers already in the mountain before the rain started falling? No, but the actual accumulation of that particular sort of statistics will produce rivers with specific statistics, branching statistics and so forth. So I'm finished with my metaphors. I've squeezed every single one of them as much as I could. It's done now. And in fact, I think that the computing brain is largely done. Next week, I'm going to talk a little bit about reinforcement learning and give you an example of a perceptron that does the matching law. I don't know if you knew anything about the matching law before, but it's also some cool stuff, I think. And for today, what I thought we could do is, you go through the Hopfield project to ask questions. In Teams, I'll be here to address them. Other questions, observations, ideas? Yes, please.
I was wondering, so when you showed us 3 blue, 1 brown video about gradient descent and back propagation, so there were this example where there was a handwritten 3, and at the end, sometimes the output from network gives estimations for 2 or 4 or 6, but at the end we want 3, So could we use Hopfield networks for that network to just go back to the state of being 3, the attractor, sort of?
Yeah. You can save characters in a Hopfield network the same way as you would, right? Only that. So I'm not completely sure. So I'm not in a fixed forward neural network. You can also talk about an attractor, but they're always very trivial, right? You have an input-output relationship, and that's a strict input-output relationship. Whereas if you have you don't put random stuff on the input like you can in the Hopfield network.
Yeah, but if you do, for example, if you have a Henderson 3, but you put some stuff on it, for example, random things, but you want at the end to get the 3. That's what I was asking. So if you so that will work.
Yeah, so that's what the Hopfield network would be able to do, and it goes forward in metaphor, because ultimately, what's a 3? A 3 is not a conjunction of pixels. It is kind of like a broad idea. If you save too many types of 3s in a Hopfield network, it will get very confused very quickly, because it's dealing with pixels only. We'll have to think about the problem a little bit more abstractly, potentially, to have a network reconstituting, for instance, the contour. Right? And these are the networks for the basal ganglia of the type that Nengo has put together. They use the idea of attractor networks from Hopfield networks, but they go a little bit further into trying to detach themselves from the pixel input and understanding what are the intermediate layers of the encoding. And they think about, for example, as the 3 encoded also as a motor pattern. And then it can be different every time. And you can even use that motor pattern to constrain the visual understanding. So the more 3s you've drawn, the better you can actually understand the number 3. Children still confuse 3s with E's, no? Because that symmetry can only come once you use data from other sources to continuously constrain that network. Many of the examples we use are visual, and so a lot of stuff here has to do with pixels. I mean, the next level here will really try to separate ourselves from the pixels. But as a first approximation, the Hopfield network can create dynamics towards fixed point attractors, no matter how you conceive them. They could be parameters in something else. You know, it can be, they definitely don't necessarily need to be pictures. So you could parameterize a hidden state on a manifold. But this brings me a bit farther. So, but I guess that you get this sense. I mean, like, these are all Lego bricks, right? So you put them together. Now I'll put the Jechter-Weiligers. Thank you for the question, because these are really the essential ones, the discussion questions. And you know, this is the thing about BCI. If the activity weren't reproduced, then we couldn't read it. It is reproduced, and is reproduced in ways that are meaningful. So even if there's drift and change over time of the brain, we can, for a little while, use the activity to represent an output. And I think that this is really well represented by reservoir networks. So reservoir networks, you know, you can extract from them information from the output once you get information from the input, once you profile the dynamics for long enough. But now I'm belaboring. I like to talk about these things, and so I'm just going to continue until I stop myself, which is now. Any more points of discussion or questions, suggestions, thoughts? Coolio. Okay, I'll stop the recording for now. And I'd suggest, if you guys have the moment, to just, you know, let's meet in Teams and start going through the project on the Hopfield networks Necker cube. Hopefully this will give you a little bit more of a sense of it. You can do one or two things. You can also go simply to Jechter-Weiligers' blog and just play with the Hopfield network there and try to understand what is at that level. So now I think the material has already been delivered. So just about honing your newly acquired conceptual space. Julian.
Is it true that I can't find the lecture of Wednesday yet?
So that was the Habian learning lecture?
The deep learning one, the one after.
Yeah, I think I have to download them and upload them now. I'll do.
Okay, thanks.
This is in my backlog.
I think the pattern recognition lecture is in YouTube playlist, but under a different name, like
Is it?
FFWD.
Okay, let's see. So this is I have the lectures here. Feed-forward networks, hierarchies, and invariances, part 1 and part 2.
Yeah, that was the one, right?
Yeah,
The
I think
Tuesdays.
so. I think so.
Yeah, because I opened it, I think, and it was that, as far as I remember.
Yeah, Julian, those?
That one is the one of Tuesday, right? The FFWD, and I want the one of Wednesday. Because that one ends with me talking, and I'm the one that I missed, you know.
And so let's see. So what day was that?
Wednesday. I think that's the day we did the TensorFlow playground, and before then that you
Yeah.
had a little bit part of like pattern recognition, continue creating the
Okay, yeah.
discussion.
I missed that one because the Tuesday one was the one that we discussed the project.
Okay.
And
What day was Wednesday?
13.
Oh, I have bad news for you. Didn't we record it? This should have been here.
Did I miss a lot?
Well, the good thing is that I already have I have a TensorFlow playground pre-recorded video with similar content from the past. So
I tried the playground, but
this one.
I failed. Oh, well,
So did you see this video?
no.
No, I'm gonna put it in the TCB list then. So I think you can go through this. You tried the because people I think were largely very successful, at least in the groups. So that information should also be in Teams. Now go through this video here. And then I guess that I explained at least the general idea and what were you doing and how to produce things, or at least that's the what are the receptive fields. I don't think we've recorded the feedback session. Sorry, Junior. Did you see the answers here? Yeah, here I also have like some answers to the classification too. So I think we go through some of them. This is actually an output. I think have a look at this and see if it helps. If it doesn't, then we can also continue talking next week.
Thank you.
Okay, now I will stop the share. Wish you all a phenomenal day. And to myself, less pain. And I'll see you later next Tuesday. We're going to have a bit of reinforcement learning, a bit about manifolds, like some things that we left behind dangling that I think are interesting. And one thing about the matching law. So talking a little bit about trained decision making. All right. So, and then on Wednesday, we have the prep for the night of the BCI, and I'll have the video online, and I hope that you can enjoy that. Nothing further to add. So, thank you, Laura.
Bye-bye.
Bye.
Get well.
Have a good day.
Thank you.
Thanks, Mario.
Thank you, everybody.
Yes, thanks.
Bye-bye.